Hello, good morning. Welcome to Krishna's classroom. Let us resume our lecture series. We considered the well-known bounded convergent uniform boundedness theorem, and now we take up the another important theorem in Banach spaces, namely the open mapping. What does it say? It says, suppose there are two Banach spaces and you have a bounded linear map from one Banach space into another. And we also assume that this particular map is onto. Then what we can say is that all open sets from the domain space is mapped onto open sets in the range space. Okay? Right? So that's the statement of the theorem. Now, as I have written here, bounded linear mappings from a Banach space onto another maps open sets onto open sets. So this is the content of the theorem, and it is for this reason that is images of open sets are open sets. Now this is the reason why this theorem is called the open mapping theorem. So we shall examine one after another the conditions of the theorem. So we shall put it in symbols. If x and y are Banach spaces and T is a linear transformation from x to y, and you know that all bounded linear transformation, T is not just a linear transformation from x to y, but it's also a continuous linear transformation, or equivalently a bounded linear transformation from x to y, which is onto, and if A contained in x is an open set in x, then the image of A under T in y is an open set. Now this is the more precise statement of the theorem. We shall prove a apparently different version of this theorem, which in turn implies all this. Okay, so let us give the statement of the theorem. The statement that we are going to or the version that we are going to let x and y be Banach spaces. Needless to say that they are Banach spaces over the same field. Let u and v be the open unit balls in x and y respective. Let T belong to is a bounded linear transformation from x to y, which is onto then there exists a delta positive such that E of U, that is the image of the open unit ball in X under T in the vectors in the Banach space Y contains delta V, where delta V is of course the set of all delta times X, where that means it's a open ball of radius delta. It's an open ball of what it says is that there exists a delta positive such that the open ball of radius delta is contained in image of U under. Okay, let us be a bit more explicit and get a visual feeling of it. Now, this is not R2, this is the representation for X and this is the representation for Y. Both are Banach spaces. Okay. And what you have is U, it's the open ball radius. This is U, interior of this. I mean, this is to show that the boundary is not included. Just wiping off or make it a sort of boundary which is of dots. Similarly, you have unit ball in same way. The boundary is not included. These are the open unit balls. It's actually the interior of the closed unit. That is V. radius 1, here also radius. Now what is this? What is the statement of the process? You look at the image of U under T. What is that? That is going to be some set. Depends on T. But what you can say is that T maps 0 to 0. This is the 0 element. So you see that this is 0 in Y, this is 0 in X. You want, you can write. That's the image set. Okay, so this is 0x. This is now what we want to assert is this, that the 0 in Y, which is a part of TU, okay, so 0 Y is contained in T. Okay. It's not OY, this is 0 Y. So 0 Y is contained in the element of TU. Okay. Okay. The element of TU contained in. Now what we assert is that this is it's an interior point of this is an interior point, that is 0 Y is an interior point of in other words, this is it. There exists a neighborhood of 0 Y T. Okay, how is this stated? So you cannot say that TU is essentially contained in V. That we cannot say. But what we can say is that, you know, that OY is a point of V. So what we want to say is that there is some neighborhood of, some open neighborhood of OY. Okay. There is some open neighborhood of Y. Okay, which is completely contained inside V or Tu. Okay, that means containing Tu. That is, there exists a delta positive such that delta V, which is a neighborhood of y, this is the statement of the thing. So this is what you do. This is the statement. That is, delta V is this is what we prove and call this the open mapping theorem. So we shall ask, how does this imply that open sets are in this is the question that you are asking. So this is the central question that we are asking. Okay, so we shall prove this. So assume the statement. See, there are things like the mapping is onto, etc. I shall comment about it and even give an example which highlights the importance of that onto. But let us not bother about it. Let us assume that the theorem is true under the conditions given. Then assume the statement of the theorem. Let show that So what does it mean? It means that what is that you have to do? So you have, suppose this is A, this is T A. Want to show that this is open. Okay. To show that this is open, what you do is choose an arbitrary point y belonging to P A. We show that there is an entire neighborhood of y contained in T. Okay. Sufficient to prove that for any y belonging to P A, there exists an epsilon neighborhood of y contained in T A. That is a set of all y1 epsilon is contained. This is what you want to. So this is the epsilon neighborhood of y. This is set of all y1 such that the distance between y1 and y is less than epsilon is contained in, or some epsilon possible. This is what we want to. How to pick the epsilon? This is the problem. Okay. What we are assuming is the statement of the theorem. So eventually we prove that statement of the theorem so that it will imply this. Okay. So we have chosen y belonging to point of T. Then T being onto, there exists x belonging to A such that equal to such that Tx equal to Okay, let me just slightly change the notation. Sufficient to prove that for any y naught belonging to A, there exists an epsilon neighborhood of y naught such that is this. So this is the epsilon neighborhood of y. Okay, so this is y. So then there is some x naught here. So that x naught is mapped to. That is clear because it follows on to statement. Now we have to show that there exists an epsilon neighborhood of y naught which is completely contained in TA. We can use the statement of the theorem that we have assumed. Okay. So how to do this? See, the first thing that we do is we change the game by translating these open sets. Now note that we translate any open set in X and Y are open sets. Let A tilde it's not or we will put it this way. Let okay. Translator minus x naught. Then what you have? Then 0 belongs to A tilde. Then 0 belongs to A. You are just moving it backwards. Okay, to x naught. So it's something like this. This is the vector x naught. Now you move this whole thing as it is. This is the translate of that. Okay, so what happens? This x naught is moved back to 0. So 0 belongs to this is A tilde. This is A. So you are just shifting it back to this vector x naught, minus x naught along minus x naught, then you get x naught gets shifted to 0. So 0 belongs to A tilde. Now you see that you get T of or TA tilde is the translate of TA minus y naught. Okay. So when A gets translated to A tilde, there is a corresponding translation of TA getting translated to TA tilde. TA tilde is essentially the translate of TA through minus y naught. What does this mean? This means TA tilde and zero. Okay. So it is sufficient to prove that so this is what you have. So A open in X means A tilde is open in X, and you want to show that TA tilde is open in X. So what we do, we use this result. Remember this x naught is an arbitrarily chosen point. So sorry, y naught is an arbitrarily chosen point in TA. Okay. Therefore, for each such choice, whatever statement that we make is true. Now, what we claim is this. There exists an epsilon neighborhood of 0. That is an epsilon neighborhood of 0y. If you want, you can write this as contained in TAT. This is what we want to. So what you do is the following. Okay, by the theorem, delta V is contained in T of. Okay, delta V is contained in T of. This is the statement of the theorem that we are going to use. Okay. Now, what we do is you open and 0x belonging to U implies there exists a delta positive such that delta of V is contained in U. Now this delta V need not be in A to E. Delta V A to E. Okay. But being in 0x being an interior point, delta U may not be, but 0x being an interior point, there exists an epsilon 1 positive such that delta epsilon 1 U is contained in delta epsilon 1 U is contained in Delta epsilon 1 x belonging to U. Neighborhood of B. No, by the delta epsilon 1 B is contained in P of epsilon 1 B. Okay, so this is the result that we have. Okay, consequently, epsilon 1 V is P of 8. Now this of course is contained in P of 8. Okay, in the image of which is contained in T. Okay, and now you translate back. The implication is that implies translating to y naught, we have T a tilde a there exists and epsilon 1 there exists entire a. I think now what we have y naught contained in T. Chosen point in TA follows that every point is an integer. That is the ace of so what we have proved is that if the statement of the theorem is true, it is such that T maps we have T maps open sets in U in X onto that's why, and remark this justifies the title of the theorem. The open mapping theorem. So that justifies the title of the theorem, namely open mapping theorem. Somebody says that open sets are mapped on open sets. Okay. Now, one thing that you observe is that, so we make some interesting remarks. Observe that we have assumed what have we assumed? T is we shall observe that the absence of this assumption conclusion of the theorem may not be valid. Conclusion of the theorem may not be. We'll take an example. To highlight this, we'll look at the example. Consider T from R2 to R. Both are, of course, Banach spaces. T defined by zero. That is, T is the projection operator onto one axis. You have the one axis and the two axis. That is, we can give a picture of this. This is the orthogonal projection that we are familiar with. If we have chosen the basic coordinates orthogonally, suppose this is the one axis and this is the two axis, and this is the point x1, x2, then this map 0 along this axis 2 is what you call the projection onto the one axis along the two axis. Now T is not onto as a map R. Okay. Now let us take consider it is, I guess, such that that's right. Less than T of B1, this is equal to what? This is the interval minus 1 to 1 contained in line segment the line joining R. This is the projection. Even given. Now, this line segment has a subset of not okay. This is a consequence T is not onto. It's only a proper subset of, that is the range of is a proper Now we look at the same transformation in a different way. And we will see the difference. Let us look at different way. Let define x1. This is equal to x1. Now this belongs to R1. Now E of this is equal to the interval minus 1 to 1. This is open. The interval minus 1 to 1, which is open in R1. This becomes to and there's a small confusion that you may encounter here, because here I have written a pair of points minus 1 1. Now this is in sorry. This is the interval, the line segment. Okay, I have explained it. Okay, right. So T being onto R1, the theorem that is, this is the open interval. So T maps the open ball to the open interval. Okay. Whereas if you look at the same problem as a linear map from x to x, then the scenario changes because the map is no more and okay, I think that's a very nice place to stop. So we are now left with the proving the statement of the theorem the way in which we have asserted. Okay. Thank you very much.